Hello, welcome back. This is a quick tutorial. I hope that is going to be quick, but it's a quick tutorial on how to use the UTCI template for you to conduct your analysis in your site. So first of all, you'll see in the resources this file called Vuurparken 3D Model Simplified. And basically this file has a very simplified 3D model of your site. There is no topography considered because the site, although there's a little bit of a slope, the site is quite flat. So for simplification reasons, we just assume that it is flat. So here we have all the blocks that surround Vuurparken, and we have a couple of dots here, and some of the dots are red and other are magenta. And if you see the structure here, the layer structure, the red dots are the location of conifers. So this is evergreen trees such as pine trees. And the magenta dots are deciduous trees. So this is the location of deciduous trees. So and where did I get this information? I got this information because I imported the PDF of the site plan to the site. So if you click on this layer, this master layer in Rhino, you will see the entire site or the entire 2D drawing imported into Rhino. The 2D drawing that was in a PDF format. There's a bunch of layers that I just turned off because there was a lot of information, unnecessary information, and it would just like clutter the model. So I modeled this based on the PDF of our site plan. So, and the way that I distinguish this is because there was a type of block for deciduous trees and a type of block for coniferous trees or evergreen trees. Um, as I told you last class, when we are in computer world, I'm just going to show you that because I'm not showing the grid axis. When we are in computer world, positive y-axis, it means north. And this plan is oriented, already oriented in north. So you don't need to tweak with it. So I'm just going to delete that unnecessary information. So we have this. So this is the existing location of this point collection. And then you have this quite simplified models, two types of coniferous trees here, which you will not use. This is a little bit outside the site because we are just going to, you'll see in a while, use in this information to populate this point. And then there is this three other types, which are the deciduous trees. Okay, there are very simplified models. I run a bunch of tests with more interesting models like this one, which is a 2D model that is being rotated with the copy option on. But it turns out that when I ran a couple of the simulations, it turned out to be quite slow. So this is kind of like models of your trees that you can populate on the site that are efficient as as the best that we as efficient as we can get to a very, let's say, a very big model with a lot of geometry. Okay, so this is kind of like the structure of the model. You also see that here the building masses are stored in a layer called building masses. The garage masses are also stored in a layer called garage masses. And then you have this type thing here, this thing here called analysis plane. You might delete this, it's fine. Or might delete, no, you might turn off the layer, it's fine. But basically, these are the spaces that we are going to conduct our outdoor thermal comfort analysis. Okay, so this is the structure of the layers, the information that we have here, and the information that we are importing from Rhino to Grasshopper. When you open the Grasshopper UCTE template, you will find this big Grasshopper definition. Okay, and parts of them they're hidden because. For example, I'm using clusters that simplify a little bit of the code, but the one thing that you need to know about this template is it gives you kind of like a description. What is it? It's a urban thermal conference script that I made last Friday. I finished last Friday, and I was fine tuning today. And this part here, as you see here in my screen, I can just draw this part here. Here, it's just geometry. Okay, so this is conifer, and this is the trees, and this is building context. Okay, and this is the analysis plans grids being imported into the file. Okay, for the purpose of using this template file, you need to first open the Rhino file and then open this template file. So first thing to memorize is this is geometry being imported. Okay, this here, this portion here is calculation. So here I am processing the data in different ways in order to get in order to compute outdoor thermal comfort. Okay, this part here is processing the data and visualizing the data. Okay, you will see that in this part here you will have red components and orange components because we didn't run any type of simulation. So these guys are kind of like waiting, they're hanging fruits waiting from some data to be fed into them. Okay, sweet. So where are our trees here? Instead of like copy and pasting manually and then import a bunch of geometry, what we are going to do is apply the prosy concept. So we are just going to process each tree and then just copy using Grasshopper into this part, into their specific locations. So, for example, another thing before we jump to the way that this file processes geometry and run the simulations is that everything that is marked within a green group, like this here, like this here, like this here, like this here, is the only things that you can tweak with the model. Okay, it was for you to tweak with the rest part of the model, you need to have a lot of expertise on visual programming and in Grasshopper. So I would not recommend you to tweak with anything else in the model. If you think that you need to tweak with anything else in this script, shoot me an email or just swing by my desk. Okay? Okay, so here we have coniferous point location. So I imported from this file these points here, as you can see here. These points were imported from the file here to this here. And then there's an empty BREP component or geometry component. I forgot which component here, which you can add other points for coniferous tree locations. And then you set those multiple points and then you connect it here in this merge list component here. Okay, this is the way that you work with this guys here. You don't put this is just like to give variation of what would be the type 1 and type 2 probability. So there's two types of coniferous. One coniferous that has a bigger canopy than the other, has a more spherical canopy, and the other has a more conical canopy. Okay? So it's fine. You just need to define new points or new location points for those conifer trees, for those pine trees. Okay? So conifers are evergreen trees, so they are non-deciduous. So they always have their leaves. So that's why we only have one group of conifer trees. The deciduous trees are different. We have one group for the winter condition and one group for the summer condition. Okay, and we need to have those two groups because we are just going to make a simulation that runs for the entire year, and we need to have the data for part of the year and when the trees have leaves, and the data that's or for the other part of the year when the trees don't have leaves. Okay, so that's why we are doing this kind of like in parallel. That's why you run two simulations and you will see, and then we cross the data, we filter the data and compose the data. Okay, so this is the first part here, and here is the same thing. So both for winter, both for summer, you just need to make sure that every point location that you give here are the same. So one way to do it is, for example, just use one and then connects here and connect in the other one. Okay. So let's look at the difference and let's look at the visualization of this. Another thing is everything that is in the red circle, no, magenta circle is components that you can turn on the preview. So I'm just going to turn on the preview on this one, and you see that something popped up there, and I'm just going to turn on the preview of this one, something popped there, and I'm going to do for the winter situation, just for you to see what is being modeled and what is being imported, okay, or being considered. And here you have evergreen trees, non-deciduous trees, our pine trees here. Not all the geometry is carved out because there are leaves, okay? Not all the geometry of that cone or of that kind of like a skewed sphere is opaque, right? Because light can go through the leaves, through the blank space or through the voids between, or through the space between the leaves, okay? Here in the non-deciduous trees, you might argue, why are there some leaves here? Well, here in the winter condition, because we are seeing the winter condition, only 10% of the leaves are within the tree. And this is just to simulate the effect of the branches. Okay, instead of modeling the branches, which would be quite tedious, and would probably also overload the simulation with a lot of geometry. This is an approximation, okay? So I just use the same, but we just remove less percentage of foliage in this canopies, of leaves in this canopies. So this is the winter condition. You can see if we put in a top view, you can see that the evergreen trees are quite, robust and full of leaves, and you see that the deciduous trees have very few leaves here. Okay, so if I want to see the summer condition, just for you to, and you don't need to have this, but it's just to visualize what is being considered in your exercise, you'll see this here. Okay, so the deciduous trees right now are full of leaves, so they produce more shadow. Okay, sweet. I'm going to just turn off the preview of this. Very good. Now, you have two types of context. One for the winter season, or one for the period where the deciduous trees don't have leaves or have less leaves, and one for the period where the deciduous trees are lush, they bloomed and they're full of leaves. Okay, so there's different types of context: the winter context and the summer context. And we will run this annual simulation because Ladybug only allows us to run outdoor thermal comfort for the entire year, for in parallel, assuming the winter context and the summer context. And after that, we will remove and combine the two into a year where the trees in between April to October have their leaves on. And outside that time range, they have their leaves out. Okay? So this is how we are handling with the context. Another thing that you might consider is to import more building context. Imagine that what would be very, very cool is to make this buildings taller and project more shades. If you find out in your analysis that shading is a big thing, or that shading will improve thermal comfort, and you need to have a good, you just applied good common sense, and based on the climate analysis that we did last class, you might you might say that shading is a very good thing, or shading is not a very good thing. So this is important for you, because you always need to be critical thinkers. So you need to think, if I need shade, I might put more trees. If I need shade, I might raise my buildings, or even if I need to block the wind, I might raise my buildings. But by raising my buildings or putting more trees to block the wind, for example, using the coniferous trees, as we look last class and discussed last class, coniferous trees and evergreen trees are trees that are more effective. Are the only trees that are effective to work as windbreakers. Okay, so that's the catch. If you want to block the wind, you're going to produce more shadow. That might be good for certain climates, that might not be good for other types of climates. That might be good for certain periods of the year, that might not be good for other periods of the year, and so forth. So there's no panacea, there's no magic pill that will resolve all the diseases in the world. So there is no magic solution that solves all the problems in this regard. Okay. So if you want to increase the building, you might just like scale this thing. It will update here, or you might add the building, and then you just import that again. You just need to import all the buildings again. Okay. If you model in Rhino, please make sure that you model in here in building masses, and you can also kind of like import, select all the objects in this layer here. Select objects in this layer. Okay. Very good. You don't touch this, and you need to touch this. I am very sorry. This should be in green. I'm just going to put this into green. Why? Because this will appear in your computer as orange, because this is where I store my weather file from Odense here. So you need to browse to your local machine and select Odense's weather file here. Okay, sweet. Let's keep moving. So everything is set and done. For your base case, you first run the analysis of the existing geometry of what you have here. Okay, you first run your analysis case. This is the best baseline case. Okay, then you might think about like adding some buildings, making the buildings bigger, adding some windbreakers. You could add more geometry, and you put it here in the building context or in the garage context, whatever, in order to break the winds, etc. Although wind, and this is very important for you to know, wind is not being the UTCI model, or the way that Ladybug is doing the UTCI model, is that it's just using the weather file data. So if you're just increasing the buildings in order to block the winds, or put more trees to block the winds, we need to kind of like trick the simulation in order to assume that those points will be protected from specific types of winds. Okay, there we go. So, um, so you have this, you have this, so everything is set in place. So to run the base case analysis, you go to the switch panel, or to run any type of switch analysis, you go to this big switch panel. It's like an electrical switch, and you do it sequentially, okay? Or else it will make your computer very slow. The simulations I run in my machine is quite good. They take up to 5 to 10 minutes to run. Okay, so let's turn this first compute sky exposure to true. When you double click on this toggle, the true, it only appear true when it completes the simulation. Okay? There you go. So you already compute the sky exposure for all of the points. Okay? All of our analysis points, which are here. If you want to see the analysis points, I'm just going to turn this thing on for you to see the analysis points. It's the green ones, okay? Are these ones here. It's a grid spaced in each of those analysis plane 10 meters by 10 meters, okay? There's 268 analysis points. So you compute the sky exposure, so how much of the sky each point is seeing, okay? Then knowing that, we can compute mean radiant temperature. How much is the temperature being corrected, or the air temperature being corrected, factor in solar radiation, which depends on the sky exposure. And this takes a little bit more time to compute, this too. So let's click this to true and wait a little bit. You see the mouse wheel sometimes turning into the mouse icon turning in this to thinking wheel. This is a good sign. And just be patient. It's not a lot of time. Taking my machine, the overall process of doing this takes like 6 minutes, probably in a slower machine 10 to 12 minutes, which is not a big deal. Never move grasshopper canvas when these computations are running. It's a good practice to do. Don't do anything in Rhino or in Grasshopper while this is computing, thinking. Okay. Only move or only start interacting with Rhino or Grasshopper when you see the toggle turn into true. When it turns to true, it's because the computation is done. Okay, so solar mean radiant temperature. So the effect of mean radiant temperature and air temperature is being calculated. Now we have everything. We have air temperature, we have winds, we have relative humidity, we have corrected solar mean radiant temperature. We can compute right now, we can calculate the universal thermal climate index in order to estimate what will be our perceived temperature and what would be our thermal condition, how we perceive the outdoor environment thermally. So this probably is the one that takes a little bit longer to compute. So let's turn this into true. Okay, we have it's done. In my machine, I think it took 2 minutes and a half. Not a big deal. So right now everything is calculated. Okay, so the baseline case here is calculated. You just repeat that process into your local machine. Very important thing. I'm going to repeat. Very important thing. Every time that you want to tweak, add geometry, change, or propose a new solution for these spaces, before you do that, before you import the geometry to this component, please turn this into false. Please turn off all of these toggles. Okay, switch off these toggles, because then it will become extremely annoying, because every time that you move something or every time that you add something, it needs to redo these calculations all over again. Okay, so this is this. So here it calculated for the entire year, assuming that the trees are deciduous. They don't have, assuming that the trees don't have any leaves here, winter case. But it did it for the entire year because we cannot control here. We cannot control here the schedule when we are running this. Okay, it always runs for the entire year. So here we run the sky relationship, the solar MRT, as we saw in the small template file that we use in class, and here it calculated UTCI. Okay. Um, Here it did the same thing, but just assuming that the leaves, that the deciduous trees always have the leaves. They're full of leaves for the entire year. Okay, but we know that that's not true. So this part of the code, what it does is that here the assumption is that the trees will get leaves from the 4th of April, first hour. So magically in our simulation world, midnight and 1 minute of the 1st of April, the trees will just be lush. And here is the hour of the year that the trees will lose the leaves immediately. Okay, so will be the first day of October. Okay, we know that that the spring equinox is around March 21st. Some years is March 22, 23, fluctuates that, but it's around March 21st. But we know that even in the spring equinox, the trees start getting the leaves. So that's why we push it to April. The same thing is about the fall equinox. So autumn is September 21st or September 22nd, some days, some years. But here we just assume we'll just give 2 more weeks to wait that all the trees lose their leaves. Okay? This is the final UTCI calculation. So this is kind of like my magic that I did with you, that I did for you, having a little bit Python script here, doing some magic here to merge the two. And this is the real UTCI calculation here, is when, where is the perceived temperature in the period, like for the entire year, where the trees have leaves, both have leaves and both don't have leaves, okay, in different times of the year. So this is the final UTCI final calculation. This is the thermal condition calculation, which is basically say that if people feel neutral, hot or cold, and this is very important, the UTCI category. So this UTCI Celsius gives you the corrected temperature, the perceived temperature. The UTCI category will give you if people feel neutral, slightly cold stress, light heat stress, moderate heat stress, moderate cold stress, so forth. Okay? And this is done for the entire year. There's a green button here that is apply period that just filters that data for a specific period. And that might be useful when you look at the DGNB criteria, because DGNB criteria sometimes ask you to look at a couple of days or just even in one day. Okay? And you can control that by using this here. You select the month, the day, and probably you don't tweak with the hours because you want to look for the entire year. Okay. Okay, and this is the information being like this type of analysis period being applied. For now, for the sake of this tutorial, is we are just applying the period for the entire year, but this is parametric. Another piece of advice, don't drag the sliders. It's usually less efficient. If you double click in the slider and change manually the number, it's more fast. Okay. This does another magical thing that's here that I did for you. Because we know that UCTI is a point in space. It's a local metric. It's a point in space dependent metric. We have the values of the perceived temperature for the entire year, but in a very specific location in space. What is this doing here is spatially computing thermal conditions. So we will map in a mesh here how people will, how does this space be, what is the performance regarding outdoor thermal comfort for the entire year in the space, okay? And what we do that, we apply a statistical technique called dimensionality reduction, okay? So basically, instead of looking at UTCI, we just look at the percentage of time that people will feel neutral, that people will feel cold, and that people will feel hot. So each of those analysis points that I showed you in the grid before will show that percentage of time, okay? And actually it's here, and you can I put this into 1000, but it will be 100 in order just to not clutter the model, and it's here mapped. Let's look at this in a top view, and I'm going to hide building masses for us to read this graph. Okay, so this is, right now we are looking at percentage of time where people in the center of each quad of this mesh will feel hot. And you see, well, this is Denmark. You see that there's not a lot of time where people in your site will feel hot. Okay? But because it's a percentage of time, it always goes from 0 to 100. If you want to see the area that probably people will be more exposed to the sun and to high temperatures, right? You can tweak with this. So this will compute spatially thermal condition, this Python component here that I script for you guys. And this here, what it does is visualize it, okay? You see, remember, everything that is within the magenta circle is what is being seen or what is being displayed in Rhino, okay? So if I want more granularity, I can reduce the scale of this graph by just, for example, putting into 10%, okay? So I know that there's going to be very little hours in the entire year that is going to, that people will feel very hot, okay? So there you go. Here you know that this area probably is the most exposed to the sun, okay? Okay, but if you want to compare graphs, make sure that the scales are the same, because you don't want to visually compare graphs with different scales, because then they will become, especially if you're encoding value in color, like we are doing here, because we want to make sure that the same color means the same value. Okay, it's a very common mistake that I find in this type of work. Okay, sweet. So this spatially computes thermal condition. Do you see this dot here? There's a white dot here. What is this? This white dot here is this. It's the location where you can retrieve detailed hourly conditions because DGNB credit will ask you for that. Okay? Will ask you for you to select a specific location. And that's your job for you to select a specific representative location. Okay? And how I do this? You just use this slider here. So there's 268, I believe, locations. So this is an index. So we'll start at 0 and then the 267. Remember that in Grasshopper world and for 99% of programming language worlds, indexes started at 0, not at 1. So what will be the first index here? What will be, for example, 10? You just type it here. It will be here, and you'll see this white dot moving where I am going to get hourly data because this is a percentage of time. But if you want to see what is happening in this location in the entire year, you need to or want to specify where you want to see what happens for the entire year. You need to select your point in space. Okay, so for example, if we are putting here in those parts that were, if you want to expand this because it's hard to control, so you might do this. Okay, you might do expand this a lot and then it gives you more control. Okay, let's put it here. For example, let's put it location 133. Okay, so right now I'm here, and if I move my computer, you'll see that 3 heat maps are automatically being generated. The top one tells you what is the UTCI condition, and it goes from extreme cold to extreme heat. And you see that in this location, there's a couple of days early July where people feel moderate heat, very few hours that they feel strong heat. Most of the time between June to mid-September, people will feel no thermal stress, they will feel comfortable. There's a different scenario in January or in December. December is the worst month, right? People will feel moderate cold, slightly cold for a couple of hours, particularly in the middle of the day, okay? But a bunch of days with long periods that people will feel strong cold, okay? And then you have other data. Here it's kind of like more binary, although it's trinary. Everything that is white, people is where people will feel neutral. Everything that is blue, people will feel cold, but they feel cold. Sometimes they will just feel slightly cold. That's it. And everything that is red is when people feel red in that specific hot in that specific location. And here is the perceived temperature. So we know that, for example, people will feel like, although the air temperature is lower than that, but at the end, at the beginning of July, people will feel like 35 degrees Celsius. In a very cold day in January, people will feel like minus, this day here, the color, people will feel like minus 20. Okay? So this is very important for you to realize what happens in each of the locations in annual wise each of the locations in your in your site. A couple of very important things that we need to still talk about is that by principle, or let's say this, Ladybug would have these types of components that will calculate this for you. Okay, but this type of components are unable to deal with this combined data in order that I post process it in order to really represent that there's geometry that is changing across time, and the geometry that it was changing across time was the trees that were getting leaves, losing leaves, etc. And also It computes percentage of hot, neutral, cold, considering the entire year, all the hours of the year. If you're critical, you might question this, and this is what I already embedded in this file. You're not expected, or it's not expected, that the outdoor space, a public space, would be comfortable at 3 a.m. in the morning because nobody will be there. Okay, so you only want to make sure for the percentage to calculate this percentage of time where people will feel comfortable when people are using the space. Okay, so right now by default you can control this here, and I'm going to put it here for you to see. When you download the file, I'm going to edit this here. This is setting up analysis period. Okay? So right now, by default, we are just looking at daytime when the sun is up. Particularly, this fits very well here to Danish context because the sun in the summer sets very late in the evening. Okay, so people can use outdoor space 10 a.m., even at 11 a.m. for a couple of weeks. So, and sun is up in the summer period also very early in the morning. So people can walk their dog here and the sun is already up. Okay, so we have light. So this is a good assumption to make. But another assumption you might say that, I don't know. I want also to include the hours where Aunt Marie is going to walk her dog. And that could be very early in the morning, could be 6 a.m. in the morning. And I'm not considering that hour only if I'm looking if the sun is up. So you can use this to set up your schedule, but it needs to make sense. And if you use this to set up your schedule, the thing that you need to do is to pick up here hours of the year, to put it this there. Um, Schedule, period, green, and you could put it here. And the only thing that you need to do if you want to not consider sun is up, I think the sun is up is a good assumption, but if you want to tweak with this, you can just put here the custom periods and drag and it put it here into analysis annual periods. Okay, let's do this and see what happens because this is for the entire year. Oh, there's a good thing here. When you do this, custom period cannot be the entire year because I'm always filtering the list. So you can just like remove 1 hour of the year and that will be fine. It will not make a big deal in the final results. Okay. But we could just say that, oh no, it's starting hour at 8 a.m. to 9. So I'm just considering, for example, where I can put just like 6 to 9 a 6 p 6 a.m. to 9 o'clock in the evening, and I can just like plug it here. And you will not see a big impact here, but in the other bins you will see it. Okay. Let's do the same here. Let's resume to the default, which is we are just looking at the hours when the sun is up. So we're just like calculating the percentage of time where people feel hot, neutral, or cold only when it's daytime. Okay, perfect. So another thing that you need to be considering is right now we are just what is the data that we are visualizing? We are visualizing percentage of hour that people feel hot, which is very low, as you could see, right? Let's see what is the percentage of hours in our site that people feel neutral, they feel comfortable, and the paradigm changed dramatically. You see that there's a lot of space that people will feel comfortable between 50% of the daytime of the entire year to 60%. Some points people will feel more cold, more cold. Or well, we know that it's cold because when people feel hot were very little. So here people feel less comfortable here. Actually, this middle part here is actually quite good. And then what is the percentage of time where people feel cold in our space? And there you go. So here, if you go back to neutral, here you see that people will feel more comfortable here, less comfortable here. Why? It's because in this spot, people are feeling more cold. And then you can look at why is that? Well, basically there's a building here and there's a lot of shade, for example. Or this point here, this rows of look this rows, this row of location here, this part is shading by this building. Okay, so let's put it here in neutral. So this is quite useful. And then once again, you can just move, you can just select what is the location to see hourly data. Okay. Another thing is analysis periods. On this hourly data, when you select one of the locations or a couple of representative locations, could be at least three locations, would be significant, is you can just like look at specific time periods. You can just zoom in into this time period and see what is happening. For example, I'm going to select July, start day one, start hour zero, and month, oh, just a second, and month July again. And then let's put it first 10 days. Okay. And you see that this heat map changed because it's just zooming into that day. Oh, it could be less, not 10 days, but one, two, three, four, 4 days. So it's going to be four, for example. Okay, now I'm just looking at those specific days. Okay, if I want, and here becomes everything becomes a little bit weird because I'm just looking at the percentage of hours, but this graph now it's meaningless. Okay, because this graph really requires the entire year. You just when you do this, you just make sure that you're just looking at the hourly conditions. Okay, when you have the hourly conditions, it might be useful for you to copy the data, for example, of UTCI. What is the perceived temperature in terms of UTCI in Celsius? So you have this green point here called data, and you can put it here. Okay, and in this guy here, it's a data collection, so we need to break down this data collection. How can we do it? We can just use this deconstruct data. There you go, and then you put values. Okay, and this values here, I'm just going to pair this guy here. This values here you can copy, for example, and work with them in Excel. If you copy data only, I can open Excel, for example, and I can paste that data here. There you go. Okay, and I can make cool stuff with this data in Excel. Okay, I can make basic calculations with this data in Excel, avoiding grasshopper. Okay, that might be useful for you to address the DGNB point. Okay. Okay, and I think it's all. No, there's one last thing that I want to say to you. It's If you want to see the impact of removing the winds, if I'm sheltering the entire site from the wind, there's an easy way to do it. It's just you go to the winter case and you go to the summer case and you just remove here in the thermal comfort calc. You go to this thermal comfort calc here and you go to this thermal comfort calc here and you just disconnect this from the wind. I'm not going to do this because then this will recompute again and you will need to wait more 5 minutes without anybody speaking. But this will give you the impact of sheltering the entire site of the wind. I will develop an add-on for you to filter just a specific wind direction, because when you put some obstacles, you just like preventing that a specific wind direction, you just that the wind comes from a specific wind direction in the site. So I'm going to develop a little Python script for you to remove that, remove all the specific wind direction or for a given direction into the site. But this is plenty enough for you to play with this, okay? So you can make the baseline assumptions and start tweaking with it and start thinking which is the wind directions that you want to block, the sun that you want, what is the sun that you want to block, if you want to use deciduous trees or not use deciduous trees, if you want to put more coniferous trees in order to block the wind, and also to propose shade, etc., etc. But please be critical. You need to have a good hold of the climate data, and this is Denmark, and you are Danish, and most of you are Danish, and you know how it is to live here. Okay, so you know what is the hurdles and the difficulties of the climate. I'm not going to say this to you because I'm going to evaluate that to you. Okay, that's going to be part of the exam. If you were able to articulate well the climate analysis with this simulation tool. Okay, so this is it. The add-on will come really quick because now all the hard labor is done, but you can already see the impact of the wind just by doing that trick. You just remove in both thermal comfort calcs the wind speeds, and basically you're saying that there is no winds on site. Okay, so I'm able to block all the winds on site and see what happens here. Okay, see what happens for the entire year. I'm just going to set this up to the regular period. And that's it. And this is how to use this script in order for you to compute, calculate outdoor comfort, taking into consideration different metrics, point in time, taking into consideration annual, hourly detailed metrics, giving a specific location, and spatially map outdoor comfort in terms of percentage of hours in a selectual annual period where people feel hot, cold, or neutral. Okay? Start using it. If you have any questions, just shoot me, just bug me in Slack, and see you next week. Bye.